So we're going to review derivatives of exponential functions. We basically want to look at where the variable is and where the constants are. So we have four cases here, which I'll just go over. We have a constant raised to a constant because there's no variables in either the base or the constant in this example. We have a variable raised to a constant because the base contains a variable but the exponent doesn't, right? We say something's constant when it has no variables. Then we have a constant raised to a variable because the base is constant, there's no variables, and the exponent has a variable. And then we have a variable raised to a variable when there's a variable in both the base and the exponent. So the first thing you want to think about when you take the derivative of an exponential function is where are my constants and where are my variables? We have to have one of these four cases. Think about what case it's in and then go ahead and apply that method. So if I have a constant raised to a constant, well, that's still a constant, right? 100 squared is just some number. I could type that into my calculator and get some number out of it. So because this is a constant, I just go ahead and find the derivative, which is just 0, right? I don't do power rule or anything like that. So we just have here that the derivative is 0. If I have a variable raised to a constant, we have to go ahead and apply power rule, right? So we apply power rule when we have a variable in the base, but not in the exponent. So we apply power rule, we bring down the exponent and subtract 1 from the exponent, and we get this. The third case is when we have a general exponential function. So if I have a general exponential function, a constant raised to a variable, we know that it's the original exponential function times the natural log of the base. So the derivative here is the original exponential function times the natural log of the base. As a side note, notice here that if I had the function y equals e to the x, that's a constant raised to a variable. So I could do the same thing, right? I have e to the x times ln e. And when I have e to the x times ln e, I know ln e is 1, so that disappears, which is why when we take the derivative of e to the x, it's just itself. So that's why e to the x is special. We could just think of the derivative of it as just itself, because when we multiply by ln e is 1 and that just disappears. But for anything else where we have a base as a constant other than e, we have to always multiply by the natural log of the base. Last case is when we have a variable raised to a variable. We have to apply log differentiation. Okay, you can't apply any of these methods. We go ahead and apply log differentiation by taking the natural log of each side. Often I see students confuse this with taking natural log when we do L'Hopital, so just be careful. They're two different methods, right? So when we do log differentiation, we also have to take the derivative of the left side. When we do L'Hopital with exponentials and we do natural log, we don't take the derivative of the left side. So here we take the derivative of the left side because right now I have an implicit equation, right? I don't have y equals, so I have to apply implicit differentiation within this log differentiation problem. And so I take the derivative of ln of y, which is 1 over y prime, by implicit differentiation. The derivative of the right side, well, first let me go ahead and simplify that. Right, so if I have ln of x to the x, I can just bring the exponent to the front. So now I take the derivative using product rule. I have x times the derivative of ln x, which is x times 1 over x. And then I have ln x times the derivative of x. Now I go ahead and solve for y prime. So I bring the y over to the other side, I simplify x times 1 over x. Lastly, I don't want a y in my answer, so I have to plug y equals x to the x in. And this is what happens when we have a variable in both the base and the exponent. We have to go ahead and apply log differentiation. The first case that we have is a constant raised to a constant. So if we have a constant raised to a constant, meaning I just have numbers in there, there's no variables. Here I don't have any variables. ln 3 is a constant, right? If I typed ln 3 into a calculator, I would just get some number. So we don't actually know what that number is. We would have to type into a calculator, but we know it's a number. It's not a variable because there's no x in here, or there's no variable. So I have a constant raised to a constant, and a constant raised to a constant is just a constant. So when I take the derivative of that, it's just going to be 0. So if I think about the derivative of, say, 5 squared, right? That's also just 0. We don't use power rule or anything like that because it's just a constant. So the derivative is just 0. So don't be thrown off by the exponents, right? If we have a constant, the derivative is just 0. The next case is when we have a variable raised to a constant. So we could see here that the base has a variable and the exponent is just constant. There's no variables in the exponent. So we have a variable in the base. We don't have a variable in the exponent. So that tells us to use power rule. So to use power rule, I bring down the exponent, ln 3 times ln x to the ln 3 minus 1 times the derivative of the inside by chain rule. So now I have to multiply by the derivative of the inside, which is 1 over x. I bring down the ln 3, and then I subtract 1 from the exponent. This is all by power rule. And then I multiply by the derivative of the inside by chain rule, and then I get 1 over x here. So this is the second case that we'll see, a variable raised to a constant, where we apply power rule, and again, if we have a composition of functions, then we have to go ahead and do chain rule. Okay, so this would be the same thing if I had ln x to the 5th. I just try to make it a little bit more complicated here, ln 3, just to help us realize it's the same thing. Just think about ln 3 as a constant, so if I have ln x raised to a constant, we would apply power rule, chain rule. The next case we have is a constant raised to a variable. My base here is all a constant. There's no variables at all. There's only a variable in the exponent, which tells me I'm going to do the general exponential function. Well, for the general exponential function, if I have y equals 5 to the x, the derivative of that would be 5 to the x times ln 5. Or we could think of it as the original exponential function times the natural log of the base. Now, if I look at this function and I want to take the derivative of that, we do something similar. So now I take the original exponential function, I multiply by the natural log of the base, and then I also have to multiply by the derivative of the inside by chain rule. Well, the inside here is ln x, right? So the derivative of the inside is just 1 over x. So again, general exponential, the original exponential function times ln of the base times the derivative of the inside. The inside happens to be ln x here, so the derivative of the inside. So this is by chain rule and the general exponential function. The last case here is a variable raised to a variable. So here, we have no choice but to use log differentiation. To apply log differentiation, we take the natural log of each side. And I know by law of logs, I could take that exponent and move it to the front. Now I go ahead and apply implicit differentiation within this log differentiation problem. So I take the derivative of the left side, which I know is 1 over y times y prime. And then here I have to do product rule because I have ln x times ln x. So I have ln x times the derivative of ln x. The way I like to think about derivatives of a natural log function as a shortcut is the derivative of the inside over the inside, right? Because if I take the derivative of the inside, which is 1 over x, times 1 over the inside, 1 over ln x, well, that's the same thing as the derivative of the inside over the inside. So you could just think of it as a derivative of the inside over the inside, or you could just do however you do it, just go ahead and just do chain rule normally. Plus, I finish my product rule, and I have ln x times the derivative of ln x, which is 1 over x. Now I simplify, and then I move the y over to the other side. So I move the y over to the other side, and then I simplify, the ln x's cancel, and then here I just move into one fraction, and now I just have to replace my y by y equals ln x to the ln x.